mathematicians. This is Eureka Math Module 4, Lesson 7. We're going to get into some solving quadratics, but first a bit about the video. I would strongly encourage you to type this into your browser so you can access these slides as we work through them. I would also ask you to consider working with a friend. You could do it through a Zoom call and you can watch it together, or have you sit down with your parent and watch this. I would definitely recommend having either your Eureka Math printout for Module 4, Lesson 7, or have a notebook ready, because we are going to be solving some problems and taking some notes that would definitely going to need you to do some writing. All right, so I am your instructor. My name is Frank Waypole. You can call me Frank. You can call me Frankie, or you can call me Waypole. That is definitely not grammatically correct. So this video is designed for you to pause and reflect. I'm going to ask a lot of questions throughout the video, and I'm going to ask you to pause so you can think deeply about the questions. So it's not so much you just following along with what I'm doing. I'm hoping to actually engage you in some real mathematical discourse. And again, as always, please try to make sense of the math. Just getting an answer isn't the end game. The end game is really making sense and understanding what and why we're doing. In order to explore quadratics, we are going to talk about math in a pandemic sense. First off, if you or anyone you know has COVID, our thoughts and prayers are with you. We hope you are safe. So my first question to reflect on is, what business or businesses do you think have actually been profiting during the pandemic? So please pause your video and think about that. All right, so in order to launch this video and give us a context with which to think about the mathematics, we're going to watch a quick 1-minute video.
For many, Memorial Day usually means hanging out around a pool and grilling with friends and family. But with most public pools still closed because of COVID-19, there is one industry that's seeing an unexpected spike in sales. News 4's Kim St. Ange is live in Maplewood to explain. Lauren, if 2020 was like most years, this pool behind me at the Maplewood Family Aquatic Center would be open by now. Instead, all public pools in St. Louis County and St. Louis City remain closed tonight. Well, now there's this rush to find an alternative. The water is still too cold, but these two don't care.
They come out of there with blue lips, and as long as they're outside, we're happy.
Emily Bowdern and her husband recently installed this pool outside their Chesterfield home.
It's been amazing that this worked out the way that it has, because we have 3 kids, and now we can spend the summer swimming in our own backyard and staying safe.
Had they tried getting that pool put in now, they'd likely be on a long wait list.
Phone calls have been through the roof, people looking for hot tubs, swim spa.
If you guessed that swimming pool companies were profiting right now, you would have been totally correct. I can't even get a kiddie pool for my kids at the local Walmart. So next up, I have 3 pictures here of different pools, and I'm going to ask you to make some wonderings. So essentially, what do you wonder about these 3 pictures? Your wonderings could be math related. They don't have to be math related. If you have anything that you think that is worth sharing, please share it with us at Twitter. Our handle is at Eureka_math, and please tag it with hashtag EurekaWonders. So again, any questions that you have about these 3 pictures, any wonderings, please pause and go. So my first wondering has to be about this guitar. What sort of famous musician lives here that would have a guitar pool? Another wondering I have is, which one of these pools would be the most fun to swim with? Another wondering I have what's the volume of these pools? How much water does it take to fill them up? Another wondering I have would be, how on earth could you calculate the area of these pools? And finally, my last wondering is, what would it be like to build one of these pools? And that's what I'm going to ask you. So imagine that tomorrow you had to build one of these 3 swimming pools. And I don't mean a contractor. I actually mean you personally have to build one of these pools. Which pool would you choose and why? So I would definitely choose the middle pool, because I know nothing about building pools. So I would definitely want to choose the easiest pool possible. So that's how we're going to think about the math today, is we're going to think about building a rectangular pool. We're going to do things a little bit differently this time. We're not just going to jump right into the algebra. We're going to actually do it in reverse. We're going to look at the last problem first. And this is for 2 reasons. Number one, it's going to help us really make the learning stick. If we know what the end result is supposed to be, it's going to help us learn all along the way a little bit better. And then the second reason is, some of you might actually be able to solve this problem without following along with the lesson. If that's the case, then there's no need to watch the lesson. You can go right to the last slide, and you can actually start sharpening your skills with our Eureka Math practice exercises. Here is the end problem. I'm not going to read it to you, but it is about building a pool and building a really awesome kind of rectangular like patio around your pool. So I would ask that you take a minute, you read this problem. I know we haven't done it before, but I really think it would benefit if you struggled through it. Even if you read it and just have a few ideas about it, it would be better than not doing it at all. So I'm going to pause, take as long as you need, read through this problem, and actually give it a shot. If you think that you might have an answer, feel free to check your answer here. And then if you got it right, just head on to the end. All right, mathematicians. So here is our essential question. Here is the big idea that we're talking about. How can I make sense of quantities and detextualize descriptions to solve quadratic equations? That is a very heavy essential question. So we're actually going to break it down. I would strongly urge you to never just read something in math and then just kind of move forward. We always want to make sense of it because it's going to help us to learn the math a lot better. So there's a lot going on here in this essential question. So the first thing I would recommend that you do is underline any words that you don't know and circle any math vocabulary and make a connection to that vocabulary. So right now, if you have either your Eureka math printout or your notebook, this is where you would write this essential question and then underline the words you don't know and circle any math vocab and make those connections. I'll pause and give you a minute to do just that. Okay, so here's what it looked like for me. Okay, how can I make sense of quantities? Okay, when I think quantities, I think a number or a value. And I would even write that in here or draw a little picture of maybe a number. And then decontextualize might be a word that you don't know, and which we'll talk about. And then quadratic equations, okay, we've been definitely talking about that all throughout Module 4. So I definitely have an idea of what a quadratic equation is. So let's talk about the word decontextualize. If you're doing this on your own, your resources would be a friend, a parent, or maybe even the internet. So right now I think of the root word context. Okay, a context means a situation. So then I think contextualize. So I think making something into some sort of situation. And then I think decontextualize. So I think I'm actually trying to undo that situation. So that's really what we're talking about. We're talking about giving a mathematical situation and then breaking it down to see what the quantities are, what they represent, and then how we can use quadratics to solve that problem. All right, mathematicians. So here's what you need to know before we actually jump into the lesson. So I wanted to make sure that you have all the prerequisite skills necessary to follow along with us. So first thing, you're going to need to know how to write a verbal expression algebraically. So 5 more than a number. What would that look like as an algebraic expression? Please pause and think. Okay, so it would be 5 plus x. 5 less than a number. Here's where we see some common mistakes. So is it 5 minus x or is it x minus 5? I want you to pause and reflect and see if you can figure out why it is which one. All right, so if you guessed x minus 5, you'd be correct. If you guessed 5 minus x, that was an awesome mistake. So whenever I'm thinking about this problem, I'm thinking, okay, less than, that's subtraction. Something I know about subtraction is that the commutative property does not apply to subtraction. So a lot of times when I see the word a number, I'll actually substitute in a real number so that I can think about it. So what's 5 less than 8? Okay, well that's simple. 5 less than 8, that's 3. I just take 8 minus 5. So I actually have to reverse the terms. So it's x minus 5. Okay, the next thing you're going to need to know is how to multiply polynomials. We're not going to go through this problem, but we've been practicing this all throughout Module 4. Ratios and proportions. We're not going to get too heavy into ratios and proportions, but there are a few exercise problems that do revolve around ratios and proportions, and we'll address that throughout those exercise problems. You need to know how to solve a quadratic equation. So how do you solve that quadratic equation? I don't want you to actually solve it. I just want you to take a few seconds or a minute to think of the strategy. What is the strategies necessary to actually solve that problem? Please pause and reflect. So the first thing, we want to manipulate the equation to make it equal to 0. Then we're going to need to factor it. And then we're going to use the zero product property to solve that equation. So those would be the strategy to solve that quadratic. So let me ask you this. Can you use factoring to solve this equation? Is it even possible to do? Please pause and reflect. So if we were to start solving it, we'd set it equal to 0. We'd start factoring it. We'd try to split up that middle or linear term. 2 times negative 8 is negative 16x squared. We get 7x. I don't think there's any two numbers that multiply to negative 16 and add to 7. So that means, no, we can't factor it. It is not possible to solve by factoring. Here's a common mistake that people make. This trinomial, as it is written, it actually can be factored. So some students would factor right away, and they would attempt to use the zero product property even though it doesn't equal zero. So this would be a very common mistake. This is not an accurate way to solve this problem. A follow-up question, which I'm not going to answer, but I want you to think about. We can't solve it through factoring, but could we solve this quadratic with another method? So this is the first problem that we're actually going to use to start addressing that essential question. We're going to start decontextualizing this problem. These problems can be a little intimidating. I would strongly recommend that you don't just dive into reading the problem. We want to give you some strategies so that you can actually think about these quantities and develop a quadratic equation. So whenever you're reading a contextualized problem in mathematics, I would strongly recommend that you read the last sentence first. Typically, that's where the big idea or the big thing that you need to solve in the problem. So that's going to help us think when we read through it. We need to sketch a picture and find an unknown number. So I know right away I'm going to have to draw something, and I'm going to have to find a value that is not given to me in this problem. The next thing that we're going to do is we're going to call scan and connect. So I want you to just scan the problem, find any math vocabulary terms that you can, circle them, and then make a connection to them. The reason that we're doing that is that learning research shows that when we make connections to things that we already know, the learning sticks even deeper. Take a minute maybe in your Eureka Math handout and just circle any math terms and make some mental or actually write some connections to those math terms that are in this problem. Please go. So here's what mine look like. Again, I'm just scanning length of a rectangle. Okay, so I know I'm going to have to think about a rectangle. That might be the picture that the problem is asking me to draw. Is 5 inches more than? Okay, more than definitely means addition. We talked about that at the beginning. Twice, so I'm thinking multiplication. I see width, so again, I'm getting to a rectangle. Ooh, less than. Okay, that means I'm going to have to be careful with that subtraction expression. Okay, perimeter, so I know I'm going to have to do something about the distance around the rectangle. And then I have rectangle again. Is then we're going to do a slow, close read, and we're going to try to put it together and make sense of this problem. So the length of a rectangle is 5 inches more than twice a number. Okay, so I know I have a rectangle, okay? And that length is 5 inches more than means addition, twice a number. So I have 2x. So see if you can figure out what goes with the width. The width is 4 inches less than the same number. Okay, so I see less than. I know I need to reverse the terms because subtraction is not commutative. So I have the same number, so I have x, the same number would also be x, so I have x minus 4. And I know that the perimeter is 44, so I want to know every side. So I filled in all 4 sides. Okay, so I know the perimeter is 44. Here's the setup. So I know to find the perimeter, I have to add all 4 sides together. So that's going to be my setup. Now there is another potential setup to this equation that you can use. We're not going to go over right now, but if you did use it, it's at the bottom of this slide deck. Feel free to use that if you're comfortable with it. This is not the only way to do this problem. Math is creative. So I'm going to go relatively quickly through this problem. I'm using color to illustrate the like terms. If I take a step back, this is essentially an addition problem. I'm adding 4 separate quantities. Because it's an addition problem, just remove the grouping terms, and I can use the commutative property to put all of the like terms together. So now I have 6x plus 2 equals 44. I get x equals 7. Now, if that math was a little confusing, I would definitely recommend pausing and trying to make sense of that mathematics. So I know what you're thinking. I solved it. I got an answer. Next problem. However, we always want to make sure that we go that extra one step and we actually make sense of the problem in terms of the context. So what does x equals 7 mean? Am I in the right ballpark? So if I go back, remember the question was sketch a picture, which we did, and find the unknown number. So 7 is the unknown number. So if I go back and read, the length of a rectangle is 5 inches more than twice 7. The width is 4 inches less than 7. So I think I'm in the right track. All right, so now I'm going to modify this problem, okay? I'm going to cross out the perimeter. Because remember, we're talking about building that pool, okay? So we need to know all aspects of that rectangular pool. So we got perimeter covered. Now we got to talk about the area of that rectangular pool. So this is obviously not a pool. We're talking about a rectangle. 15 inches squared would be a very small pool. But instead of the perimeter, so now the problem is saying the area is 15 inches squared. Find the unknown number. So we're not going to go back through that decontextualization process because we have the same problem. We can use the same picture. This time our area is 15. what is the area of a rectangle? How do we find that? So the area is length times width. Okay, so in this problem, I'm going to use substitution 3 separate times. I know the area is 15, so I plugged in 15 for the area. I know the length of this rectangle is 5 plus 2x, so I plugged in 5 plus 2x. And I know the width is x minus 4, so I plugged in x minus 4. At this point, now we're just solving a quadratic like we've done the past few days. So I'm going to go through relatively quick this process. We're going to multiply out those two binomials. You can use the area model if you like, or the geometry model. I'm going to combine like terms. I'm going to set it equal to 0. I'm going to factor. Okay, and I get 0 equals 2x plus 7 times x minus 5. Now again, I went through that pretty quick. So if you need to go back and pause, please do so. I try to outline every step of the mathematical process. So at this point, we're going to do some thinking. Okay, whenever possible, we always want to kind of think about problems before just jumping in and doing some mathematics that maybe we don't necessarily need to do. So now we can use the 0 property to figure out this unknown value. So there's the two equations. Now when we're talking about a rectangle and we're talking about a context, especially like a swimming pool, we typically don't talk about negative numbers. The reason is because there's no such thing as a negative area or a negative side length when you're building something outside of a math classroom. So one of these equations is going to result in a negative number. Which one will? If you said this one, you would be correct. This answer, I'm not even going to solve it. I just know for a fact that if I subtract 7, I'm going to get negative 7. And I divide by a positive number, it's going to be a negative number. So that's not the answer that we're looking for. So over here, I just have to solve for this equation. I get x equals 5. Again, we want to think about what x equals 5 means in terms of the context of the problem. Okay, so find the unknown number. X equals 5 was the unknown number. So now I'm going to change this problem once more. Instead of finding the unknown number, I'm going to find the dimensions of the rectangle. The dimensions of the rectangle being the length and the width. So I would definitely encourage you to pause this video and try finding that out on your own right now. So we have the same setup. We've solved for x, we got x equals 5. We know the area is 15. So how could you use this information to find both the length and the width? What mathematical property could we use? So we're actually going to use substitution. We're going to substitute 5 in for x and 5 in for x. Here's the mathematics. We get 15 inches and we get 1 inch. So is that possible? Could it be 15 inch and 1 inch? It is possible because if you remember, the area was 15. Is 15 times 1 15? Yeah. What would be another possible combination? Yep, 3 and 5 would work, but in this problem, it is actually 15 and 1. Okay, so a quick summary. The essential question was, how can I make sense of quantities and decontextualize descriptions to solve quadratic equations? Okay, so right now I want you to think, what were some of the big ideas that we went over in this video? Remember, the question is typically in the last sentence. You want to scan and connect. Just scan the problem, make connections to the math vocabulary that you already know, set up the quadratic equation, solve the quadratic equation after you do your slow, close read of the problem, and then make sense of your answer. Please don't forget that step. We've gone over a few problems. Now we need to practice these skills, and you're going to actually have to build your pool. So if you didn't answer that pool problem correctly the first try, I would like you to try that again. Now that one pool problem is not actually in your Eureka math printout. Okay, so you can get that back from the slides and you get the answer here. There is a little extra step in that pool problem that we didn't go over, but I do want you to try to struggle through that because that's going to make the learning stick. Once you get stuck, then go to the video right here where I actually have it worked out side by side with you. So there's really 2 ways to actually complete all these exercises. Use it as a resource if you get completely stuck on a problem. Let's say you're doing exercise 4 and you get halfway through and you just can't break through. Maybe that you made a computational error somewhere you didn't realize. Then go ahead and watch exercise 4 and I'll be working out the problem with you side by side in that video. The other thing that you should be doing is you should be checking your answers. So let's say you try exercise 6. Click on that video, go all the way to the end of the video, see if you did in fact get the correct answer. I hope that you get to build the pool that you like. I hope that with what we have left of summer, you're able to get into an actual pool. And mathematicians, I hope you all stay safe and join us for the next Eureka Math video. Thank you so much.